I think everything is good. I think you can just get started. Thank you.
Okay, thank you very much. So thanks a lot for the invitation to speak at this very nice conference. It's really quite an experience, and it's really fantastic. And in particular, I love the Slack and everything. It's really quite an efficient conference that you put up. Congratulations. So I would like to talk a little bit about this field that is called the S-matrix Bootstrap, which is of course very much related to the topic of the conference, which is the field that tries to study the space of possible S-matrices for a generic possible theory. But I would like to focus in this talk on a very simple toy model, which is what we call the monolith. This is based on a paper we wrote a few months ago with Lucia Cordova, Ifei, and Martin Kruszczynski. And this is a simpler toy model. And then at the very end, I will mention some past and future work with a few other people that will include some higher dimensional, like 4-dimensional scattering of pions and other interesting objects. So as I said in this talk, I'll be focusing on a simple toy model where we will be considered 2-to-2 elastic scattering. In 2 dimensions. Yeah, so it couldn't be simpler, where we have a particle of mass m and no other stable particles. So no other stable particles or bound states. And this particle transforms in the vector representation of ON, right? So this particle is a small point, and it has an index A that runs from 1 to n. Okay. So now we want to study the space of such possible theories that includes, of course, the ON nonlinear sigma model that will describe some symmetry pattern breaking and so on. Okay, so let's formulate the problem mathematically, what problem we are trying to solve. And the problem is based on 3 simple conditions. So we can really formulate very well the mathematical problem, and then we just forget about the physics and we try to solve this mathematical problem. So the first property we have is crossing symmetry. So we assume crossing symmetry. So crossing symmetry flips S and the T channel. And in this case, because particles transform in a vector representation of ON, the various channels get mixed up once I look at them when I change time and space. So let's write what equation we have. We have that the S-matrix, there is an index A because we can scatter in the anti-symmetric channel, in the symmetric channel, and in the singlet channel, right? You take 2 vector particles, you can form an anti-symmetric tensor, a symmetric traceless, or a singlet. And now here, you want to plug T, and we want to relate this with an equation where there will be S here. But I will use this hyperbolic rapidity. It's more convenient in 2 dimensions. So T will be obtained by I pi minus theta, whereas here there will be theta. Let me finish the formula and tell you what this is. So here I'm saying that the S-matrix in the S channel is related to the S-matrix in the T channel by a crossing matrix CAB that I wrote here, right? So that we will not lose time. So what is this theta? So if you write S, the usual Mandelstam variable, as K1 plus K2 square, then this is just 4m square cos square of theta over 2. So you see that T and S are interchanged when I change theta to I pi minus theta. Okay? So I remind you that in 2 dimensions, or I tell you because you might not be used to 2 dimensions, in 2 dimensions, if I'm doing elastic scattering, U is equal to 0. The energy and moment of initial and final particles are the same. And therefore, S plus T, I don't have plus U, is equal to 4m squared. Right? So exchanging T and S is going from S to 4m squared minus S. So how does this theta plane work out? So if I have the S plane, I have the 2 particle threshold cut at 2m squared, at 4m squared. We have the T channel cut that starts at S equal to 0, right? And then this is what we call the physical sheet, what we get on the plane once we remove the cuts. And in theta, in terms of theta, this is mapped to what we call the strip. So there is a strip. Can you read if I write in the bottom? I hope so. If not, please tell me. So there is the real line here. Here there is the real line plus IPy. And then the inside of this strip is the map of the full complex plane minus the cuts. So this is what we call the physical strip. So we will discuss functions, but we'll mostly focus on the value of the functions inside this strip between 0 and IPy. Okay? And this is how this theta plane works. And the first condition, we have three functions related to this property, this crossing symmetry. This is just how the S and T channel get mixed. This is the crossing matrix. So this is a matrix C such that C square is equal to 1. And you see that in this matrix, N enters. So that's the matrix, the N dependence here or here. This is where we see N. Different theories with different N's, that's where the N will enter. Otherwise, it's just some very simple constant matrix. So the second condition that we impose is analyticity. And that's related to this physical constraint that I said I want no other particles. So I don't want poles in my physical shape. Poles would correspond to other stable particles or bound state. So analyticity is the function, is the statement that these functions are meromorphic in the strip. So I'm looking for functions that are meromorphic down here. And this is the second condition. And then there is the last condition we impose, which is unitarity. Unitarity says that if I scatter two particles, the probability of going to two particles, which is just the absolute value of S-matrix square, this is the probability of starting with two particles in, say, the symmetric channel and producing two particles. It's a probability, so it must be smaller or equal to 1 if I'm doing a physical process. What's a physical process? It's S bigger than 4, of course, right? So it means theta real. So these are the three constraints that we have. We have three functions. They are defined on a strip. And then these functions, they are bounded on the real line, right? So in the real line, they are bounded. Then there is a crossing symmetry, right? There's a crossing symmetry constraint that relates points up and down. So in a way, it's also bounding the upper part of the strip. And then there is the statement that we are dealing with meromorphic functions. So that determines completely the problem we are going to discuss. So let me summarize here. So let me copy again so that we stress. So I have a function defined in a strip. It's meromorphic. In the strip. And now I'm going to write unitarity in a slightly different way, which is I'm going to write unitarity as saying that this 2 by 2 matrix is positive semi-definite. So I have a matrix. There are three matrices, one for each A. And I'm just going to write the statement that this matrix is positive semi-definite. Right? So this is equivalent to S. It's a fancy way, if I want to show off, to say that S squared is smaller than 1, I just write this. This is nice because then it allows me to state the question we want to ask, which is just, what is this space? So you see that this space, it's a convex space, right? Because being a positive semi-definite matrix, this defines a convex space. So it's some convex space. It is, I start with this convex space condition, the 2 by 2 matrix. I have a linear constraint here that preserves convexity. So this is some infinite dimensional convex space, and that's the question we want to ask is, what is this space? So that's the question I'm going to answer in this talk, or to show you a partial answer in this talk. But this is the formulation of the problem. Okay. So I know you are not supposed to interrupt with questions. You should wait until the end, but I really enjoy more when people interrupt during the talk. So if there is anything not clear in the formulation of the problem, unless the organizers would kill me, I would really appreciate if people ask in the middle of the talk. Don't worry about anything. Okay. So what's the strategy for finding the space? If you want to find a space, one strategy is you pick coordinates and you look for the walls. Right? So the strategy would be, let's pick some coordinates, right? For example, let me give you two examples that are going to be the two examples we are going to use. For example, we could say, let me evaluate my S matrix at some value between 0 and 4m squared. Remember, there are no bound states, and we have real analyticity, so this would be real. So we can make some linear combination of these guys. And this could be one coordinate. This could be a set of coordinates, right? You remember this guy. Here I'm using S, the value of S. This would be related by crossing to SA at 4m squared minus T minus S. So it would be related by crossing symmetry to this value. And this would define some three-dimensional region in this way. This type of coordinates, SA at 3m squared, it would describe some three-dimensional convex region. So I would have three dimensions that would be antisymmetric, symmetric, and singlets. And I would have some three-dimensional convex space, convex shape in this region. Right? Some picture like this. Another nice example that we could and will consider, because it's even simpler to visualize, would be to evaluate it at 2m squared, because 2m squared is a special point. It's a very symmetric point. It's like this 1/4 that we were discussing the other day. So this is a point which is crossing symmetric. This is another type of coordinate. So this guy under crossing goes back to itself, right? Under crossing. Crossing flips S to 4m squared minus S, right? And therefore, this here would define some two-dimensional shape, right? And this two-dimensional shape is another way of depicting this space that we have here. Of course, it's an infinite dimensional space, so there's no guarantee that looking at these sections, these 3- and 2-dimensional sections, is enough to capture all the interesting corners and kinks and edges that this space might have, but I believe it is. And I will show you now evidence that this is the case. Okay? So now I would like to see this region. I would like to show you the solution to this problem and then tell you how we find the solution to this problem. Okay? But yeah, so I'm going to show you this three-dimensional shape now. Okay, so let me then show you. So here it is. I don't know if you can see. So can you see? So this is the three-dimensional shape. These are the three axes that describe precisely these SAs that these various components. I don't know, I will rotate it just a bit more, but let me just highlight a couple of features. So at the top, you see that it has corners, right? There are cusps. There is one there. It can really use it as a weapon, right? So at the top. Then there are some edges. We can change the style. Maybe you can see it better like this. I don't know if I rotate a bit, and I don't know how fast it is to screen share. But you see that, yeah. So we have this object here. And it has a few corners, a few edges. It has a few lines that are edges that then soften and become flat. So it's a very, very rich object. And I'm going to describe in more detail what special features it has. We actually 3D printed it. I have a 3D printing of this object that I would like to show you, but it's in the office and I cannot get it. So I can show you. But I'll tell you now how we found this object. And I will tell you also why did we 3D print it. Okay. Okay, so here is the picture of this object, and already anticipating, I'm already mentioning here that this object has many amazing features. So first of all, the weapon point, the point you can use as a weapon if you want to kill someone, is the free theory. So that's a special point for sure. It's when this S matrix is just unity. So then particles just pass by each other. Okay? So I know this is an amplitudes conference, but for me, free theory is S equal 1, not amplitude equals 0, right? So S is 1 plus 2. So this would be the point, the cusp. So that would be the free theory. And then there are other remarkable points. For example, this point here, you see that is the union of the edges, which is this point here, is the nonlinear sigma model. That's a very famous theory that Zoomplitudes found in '79. And here, out of the blue, without imposing anything, it shows up in a cusp of this higher dimensional space. Right? Total, why would that be? We don't know. Okay, so let me describe how we go about finding these shapes. And I want to emphasize that there are two alternative descriptions that would be like this yin and yang. Yeah, so let's draw the yin and yang, right? So there's the yin and the yang, right? It's complementary approaches. So what is the yin and the yang? So the yang here would be an approach that would be like saying, no, you can't, right? It's let me explain what I mean by that. Whereas the yin here would be the opposite approach that would say, yes, you can. Okay. So what is this? No, you can't, and yes, you can. So the Yang is like the CFT bootstrap that I'm sure you have heard talks about. So what do we do in the CFT bootstrap? We put bounds, we explore these spaces by putting bounds. And in the CFT bootstrap, we put a bound. And what this bound gives us is an exclusion plot. So we say this is excluded, right? And these plots are based on some ansatz. And then we improve our ansatz, or we buy better computers. And that means we push the bound. And now this is what we get if we have a better computer or ansatz. Right? So what this way of thinking about this space tells us is this point is definitely not a good point. So this point is null. Right? What about a point here? A point here, maybe. For now, it's not excluded yet, but with better computers, maybe the bound will get there and we'll exclude it. And this one was maybe yesterday, but now that we bought the better computer, it's also no. Right? So this is a method of saying no, 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 and then maybe when the bound doesn't get there. What would be the yes method? The yes method would be the one that we traditionally have been using in the Bootstrap. There we say that I construct an explicit S-matrix that obeys the conditions I wrote before. It is unitary, it's crossing symmetric, it's meromorphic. So this is a good S-matrix. So no one can exclude this point. This is a good point, right? So here we say yes. Now we make a better ansatz for my S-matrix. I explore a bigger theory space and I get a better ansatz. And maybe now I can find a better space. And now I can find a point here. So now this point is yes. And what about a point here? A point here, I don't know. It's a maybe. Right? And so we will have this way of finding the problem, that there will be an original problem and there will be a dual problem. And in the original problem, we start with a bound and we go and we explore the possible S-matrix space and it converges eventually. And eventually my ansatz is not improving anymore. And then I have the other method where I will start ruling things out and saying it's excluded, excluded, excluded until it converges and it doesn't exclude anymore. And then the idea is that the true boundary would be somewhere in the middle, the true boundary of this space, this boundary of this shape that I showed you, this 3D shape. This thing here, delta, this delta in this kind of optimization problems is what is called the duality gap. And the good news for us is that because of this convexity of our problem, this duality gap is zero. Okay, it's the general theorem of this type of problem that we are studying. So actually it will close. And the statement is if I have good enough computers, the bound will converge and it will give me the perfect shape boundary of this shape. Okay. So indeed, so here's an example. So now I'm showing the two-dimensional shape. You remember that 2m squared, the space is two-dimensional. Right? And as you see, the red curves that start from above are the Yang, no, 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 no. And the blue curves that start with the inner polygon and then go up, 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 up are the yes. And you see that there's a zoom in where you can see that the blue and the red are really trapping. And there is a black curve that pretty much converged with many, many digits. And that would be the boundary of this region. Okay. Okay, so let me now describe, this is the overall picture, so let me describe in a little bit more detail how this goes. What is the original problem then? The original problem, we start with a strip, we have the physical strip, right? And we make an ansatz for a function that is meromorphic in the strip. Ansatz for a for three meromorphic functions, for meromorphic SA. Now, what ansatz? It's your choice. You can use whatever you want, right? It can be Fourier, it can be some Taylor expansion, it can be some dispersion relation, whatever you want. You just parameterize a big class of meromorphic functions. And then what do? You maximize some target. So you maximize your target f, that would be some sum of NA, this meromorphic function at some value theta star, some value here. That corresponds to say 3m squared, right? And you maximize this subject subject to the condition that we have that this 2 by 2 matrix is positive semi-definite. In other words, that SA of theta squared is smaller than equal than 1 here, where here is a bunch of points we just imposed in a grid, a very dense grid on the real line, that everywhere on the real line we have unitarity. So it's a linear target that we want to maximize, quadratically constrained, or linearly constrained if I write in a 2 by 2 matrix. So it's an easy target, but the problem is constrained. Let me tell you what the dual problem is. The dual problem is the main thing that we understood in this paper that I mentioned in the beginning. So in the dual problem, we want to put the bigger the ansatz here, the upper we go, and now we want to put a bound from the other direction. Okay, so we start with our target, F. And this F, as we said, is sum over the 3 channels, some linear combination of the S matrix at some value of theta star. Now, obviously, this is equal to, so I have some value theta star. So I'm going to write an identity that this is equal to the contour integral d theta over 2 pi I sum over A. And now I'm going to write k A of theta times S A of theta, where this Ka is any function, whatever you function, that behaves as Na over theta minus theta star. And I just have theta star and I have a contour here. Right? This is by definition true. And now, oops. Now I clicked the wrong button, but it's okay now. Yeah. And now the idea is we will take this K to assume that K is a function that has this pole but nothing else. And we will blow up this contour so as to write it as a contour that would become a contour like this inside a string. Okay, so let's do it. So after you blow up the contour, you will get an integral d theta over 2 pi I over the real values, Ka sum over A, Ka of theta, S A of theta, and then there is the integral, there is the term that you integrate Ka of I pi minus theta, the one where you come above, times Sa of I pi minus theta. Okay. Now, you already imposed something about K as a pole at Na minus n star. Let's impose that K, let's simplify this a little bit more by saying this Sa, by crossing symmetry, it is CAB times SB of theta. And C is the crossing matrix, it squares to 1. So let's say that this, by definition, let's define this K to be anti-crossing symmetric. So we say it's minus CAB times KB of I pi minus theta, of theta, sorry, theta. So it's anti-crossing, so it transforms with a minus sign and with a transpose. And then because C squared is equal to 1, this term, under this simple condition, this term, I can just double the first term. Right? And now let's continue. Now this is obviously smaller or equal than the integral d theta over pi sum over A, absolute value of Ka times absolute value of Sa, right? Nothing special here. And this is obviously smaller or equal than the integral d theta over pi sum over A of the absolute value of Ka, because Sa is smaller or equal than 1 by unitary. Okay? And so we are done, right? So now we proved what we wanted. We have an upper bound for our F, which is the statement that our F, it's this equation here, that our F is smaller or equal than the integral of any function K, provided this function K has a pole with residue Na, and it is anti-crossing symmetric. And that's it.
Sorry, can I ask a quick question? Sorry, can I ask a quick question?
Yes, yes. Please ask while I write the main formula here.
Yeah, when you switch the contour around, don't you have that S can be a meromorphic function in the strip? So shouldn't you get contributions of additional poles in the strip?
No, S cannot have poles. S cannot have poles, right? S poles correspond to bound states or other stable particles. By assumption, we said there are no other bound states or stable particles.
Okay, thanks.
Yeah. So the conclusion was this. So we have the original problem where we maximize the sum over A of NA times SA of theta star. By the way, thanks a lot for the question. It's really much more fun when there are questions. And we just proved that this is smaller than the minimization over this dual target, which is the sum of the sum over A, the integral of absolute value of Ka. So let me emphasize the difference between the original and the dual problem, right? The original is like the yin and the dual problem is like the yang. So in the dual problem, we have, it's a very nonlinear problem, right? It's an integral of the absolute value of K. So it's very nonlinear by definition, but it's not constrained. Any K, you just write a K, which you write a pole plus whatever you want, and you get a bound. So no constraint. Then whatever you want, you put better and better whatever you want, more and more freedom, and you get a better and better bound. So it's nonlinear, but it's unconstrained. So that's good that it's unconstrained. It's bad that it's nonlinear. This one, this way of doing, it's good because it's linear, but it's constrained. We have to maximize over S matrices that obey unitarity. So it's really a dual point of view, but as we said and as we saw, they converge very well. So here is the result. Now I can, the same picture I showed before, but now I can explain a little bit more what this picture is. So you see that this bound, the blue lines, are ansatz for the S matrix, and the better is my ansatz, the more I go out in the blue lines. So these are better S matrices, and the red lines are better case, better dual kernel scale, right? So we start with an outer polygon. So we start with an outer polygon. And we also start, if you see here, with an inner polygon. So that's the very first thing. And actually, these are very easy to describe. This is what you get if you say, let me assume this inner polygon corresponds to SA being constant. So you just say, I have three constant numbers. They must be smaller or equal than 1. They must be related to each other, this vector, by crossing. What the space do I get? I get this polygon. That defines the inner blue polygon. Right? So I can emphasize this is a polygon like this, right? Like this, and like this. What about the outer polygon? The outer polygon, you just say, the analog of just saying K-con, you just say Ka is equal to just the pole, Na over the pole, theta minus theta star, right? Nothing more, plus nothing. That's one bound. And that gives you this outer curve, this outer polygon here. And then if instead you say, no, it's not this, it's this, plus some regular stuff, and you minimize for this variational stuff, for this regular stuff, you get the better and better bounds. And here you also say plus function that does depend on energy, as physics should, and then you get a better and better space. Okay? So you have these inner and outer polygons. They touch at a point. Otherwise, they are the beginning, and then as you sandwich, you will converge towards the true bound. Sorry, I clicked this silly button again.
So, Pedro, maybe you can be wrapping up soon.
Yeah. Okay. So I have what, 3 minutes?
Yeah, you got 3 minutes. Don't worry about that.
Okay. So this is this two-dimensional shape. And I already told you that this clear cusp is the free theory. Then this is the point where they intersect. This is the point where the inner and outer polygon intersect. And these turn out to be interesting theories. This is the nonlinear sigma model. And this is a new integrable theory that, to our knowledge, no one yet identified what theory it corresponds to. So this is a new solution of the Yang-Baxter condition. So let me mention very quickly what this is. So first, this nonlinear sigma model, these blue points, you don't see it here, it looks smooth, but this is a cusp, it's a kink. Actually, when you 3D print it, you can feel it, you can touch it. And you can also see it if you zoom in, and if you tilt the axis, then you beautifully see that it's clearly a kink, right? It's obviously a kink. But you don't see, if you just see the smooth curve, it doesn't look like a kink. You have to change the axis and the plot range. Then you see it's beautifully a kink. And then what is the solution that sits at this kink, right? Remember, this is the solution. It's this beast down here. It's this function that it's a rational function of theta times these 8 gamma functions or 16 gamma functions. And this ratio of 16 gamma functions times this rational function was exactly an S-matrix that Zoomplitudes and Zoomplitudes had proposed in '79 to describe an integrable theory. So if we did not know about integrability, we would have found it in this way. We would not have imposed at all integrability. We would start studying this space of allowed theories, find that there are these special points after we 3D print it, and notice that there are points which are small cusps or small kinks. We go to these special points and we find that the matrix we found obeys the property that if I take 3 of our matrices that we found and multiply them in a given order, this is equal to the multiplication of the matrices in a different order. And that's totally not built in, right? I never spoke about integrability or multiplying matrices in different order or so on. And somehow the special points, like the free theory and now this Young-Baxter, is where it comes about. There is another solution of Young-Baxter that is even more mysterious because it's also a kink, although I would have to show it in 3 dimensions so you would see. It obeys Young-Baxter. To our knowledge, it has not been identified with any physical theory. It's periodic in energy. We could also identify analytically what it is. And it's periodic in energy. You go in energy and every log energy, it repeats itself. So it's a fun theory. And there is a generalized notion of periodicity. We have the luxury that in this problem, we can go to infinitely many sheets and study the analytic structure of the scattering amplitudes in these infinitely many lower sheets. That is a luxury that normally we don't have. And we see some nice fractal structures in the lower sheets coming about. But I will not show you other nice pictures. I will just jump to the conclusion slide, but stop. And the conclusions are pretty obvious. I'm happy to answer your questions now. Thank you. Sorry for going a little bit over time.
It's fine. Thank you, Pedro. Let's thank Pedro. Okay, the floor is open for hand raising. Lance, please.
Hey, Pedro, beautiful talk.
Thank you.
I mean, you can also divide theories into ones that are integrable or don't have particle production, and those that have particle production. Are the latter theories on the insides typically of the monolith as opposed to on the edge? And do you think everything is allowed inside?
Right. So that's precisely what happens. So the boundary, all the theories at the boundary have 0 particle production. And we understand why. The reason mathematically is because this problem is such that the duality gap has to be 0. The problem is convex, the duality gap has to be 0. And the only way the duality gap is 0, if you see there was a step where I said this step from here to here, it only works if S is equal to 1. So if we know that the duality gap is going to be 0, we know that S is going to be 1 at the boundary. Or K has to be 0. So either you are at a very special singular point, or you must not have particle production at the boundary. So inside are the theories that have particle production. And at the boundary, there will be the theories without particle production. The only exception is this yellow point. This yellow point has particle production and it's at the boundary because this yellow point, this K vanishes in one particular direction. But it's a particular exception. So the way we should proceed if we want to study physical theories is increasing the space, the Hilbert space that we truncate our system to. Here we studied 2, 2, 2. We should study more and more and more and more. And then I think what will happen is that inside each subsector, we will saturate unitarity. And the bigger the subsector, we will hopefully converge towards the physical theories we want. Because the same thing works in higher dimensions, where having no or very little particle production is even weirder, of course. Like in some examples that for pions, for example.
Okay, thank you. I see Nima's hand is up. Nima, please.
Thanks, Pedro. Fantastic talk. Just a quick question about something that actually came up in another discussion earlier this week. if you take like any one of your S matrices, well, anywhere, any of the ones you like on the boundary, anywhere else. I'm curious about the following question. If we take products of those S matrices, they should also satisfy all of your, I mean, the full S matrix. The products should satisfy all your rules, because we can think of them as an S matrix in n decoupled theories where we just happen to be scattered. Oh, sorry, especially for the integrable ones without any particle production. Is that product of things? Does it move you around the surface in some understandable way?
Right. So there are two types of products you could define. If you really think of product as tensor product, right? Then of course the particle is no longer in the vector representation, right? Because I start with vector, now I have vector times vector. Right?
True. Yeah.
Now, if I have, however,
but what about the singlet part?
Right. So let's look at just a singlet part. Then indeed, if you have a solution that, for example, has no poles, if you square it or if you multiply by another solution, that's also a solution. Those are called CDD ambiguities. And what typically happens is that, for example, they could correspond to resonances. They introduce zeros in the strip. So depending on the problem will fix for you what this ambiguity is. And in some problems where you, for example, you impose that you have some type of resonances, then you fix the ambiguity in this way.
You fix it, but I was just wondering, I mean, it's in the space somewhere, right? So if I take two things, I was just asking you, if I take two S matrices on the boundary and I look at the sort of dumb thing I get when I get the product of the two of them, where does it end up in this space? That was the question I was asking.
Sorry, you go inside. You go inside, yeah.
Oh, you go inside, okay.
You go inside, yeah. You multiply by this CDD because these CDDs factors, they are bounded, of course, by the same reason, and they are smaller than one inside.
I see. Okay, thank you.
Okay, I don't see any other hands up. So let's thank Pedro again for that very beautiful talk.